running ML models on large GPU clusters is really, really hard. To the point where uh, uh, almost every large model is a really big research publication, right? And companies like OpenAI and Google have teams of hundreds of people not doing the ML but doing the distributed systems engineering to figure out how to map that ML onto hundreds or thousands of GPUs. And at the heart of it, the reason why you have that challenge is actually pretty simple. When you're taking this really, really massive model and you're trying to fit it on a bunch of these tiny little devices, you're just using the wrong tool for the job. And so a lot of what how we think about the problem here at Cerebras, coming back to this whole co-design and vertical design, is you got to right size the problem and right size the tool for the problem.
Welcome to AI in the Real World. I'm Steve Vassallo, a general partner at Foundation Capital. In this series, we talk with leading AI researchers about their groundbreaking work and how it's being applied in real businesses today. Joining me is Sean Lee, co-founder and CTO of Cerebras Systems. I've known Sean since early 2016 before leading the Series A investment in Cerebras. At the time, Sean was just wrapping up a 3-year stint as chief architect for the data center server solutions at AMD, which he joined via AMD's acquisition of his last startup, SeaMicro. Sean is one of the biggest brains I know in and around hardware systems, bringing a rare expertise and passion for advanced architectures, many of which break from tradition and traditional approaches to computing. In this episode, Sean guides us through the world of AI hardware innovation. He breaks down the concept of wafer-scale processing, the challenges of building monstrous AI chips, and the massive potential of sparsity. He offers valuable lessons from his journey as deep tech entrepreneur, including the importance of thinking end-to-end and planning for scale from day one. We close by peering into AI's future and sharing advice for founders taking on similarly complex system-level problems. It was a really fun and insightful discussion that I think you'll enjoy. And now, here's my conversation with Sean. Welcome, Sean. Thanks for joining us.
Thank you for having me, Steve.
Awesome. Well, maybe if you could just kick us off, Sean, with a quick potted bio, your kind of background and how you found yourself in, I guess it was kind of 2015 when you and Andrew and your 3 other co-founders really got started on this idea that became Cerebras.
Well, so if you think back in the 2015 timeframe, that was at a time when the term AI and ML was still not what it is today, right? Where everybody knows about it, but it was right at the kind of the beginning of the modern AI era, where we started to see models pioneered by like AlexNet, which was one of the very first models that was deployed and trained on GPUs. You're starting to see these much larger ML neural network models than the industry ever seen before, and they're getting insanely good results. Right, starting to get results that were almost like magical, and I think that was what captured our attention. Um, just because the ML is by itself just really cool, right? Seeing back then it was all about ImageNet and being able to recognize images. Seeing that these models could actually do things that felt like only humans could do before was really magical. But what was, I think, very different about this particular workload than things we'd seen before was the fact that the only way that AlexNet was able to achieve what it achieved was that they figured out how to run these neural networks on GPUs at the time. One of the very first models that figured that out. And so it was very clear, at least to us, coming at this from the computing world, that this was a very, very special application and software workload that had such a tight dependency with the underlying hardware. And in fact, that paper, that AlexNet paper, which is now like a very seminal paper in this space, showed that there was almost no limit to how much you can push this. You make the model bigger and deeper, and it just keeps getting better and better. And that's what really captured our imagination. And so we thought that there was going to be a huge opportunity here, to build something that was specifically for this space, right? The that team figured out how to use a graphics processor, to run neural networks when everybody else was using CPUs. Um, and that helped a lot. So it's, less bad than running it on general purpose CPUs. But we just asked ourselves a very simple question: well, what if we were to design something from scratch that was made just for this workload? What might that look like? And then that's ultimately what got this all started. And then, one of the biggest things that we took a bet on was, these models are going to be really big. So we built a really, really big chip.
Yeah, yeah. Well, I think I remember one of our get-togethers. This is probably 2015 timeframe. It was before certainly you guys had even incorporated, and it was this observation of the workloads growing far far faster than Moore's law. I mean, we've been talking about Moore's law beginning to sort of slow or decelerate really for some time, but you guys were seeing this. You're seeing the workloads, and it wasn't just workloads at the sort of hyperscalers. It wasn't just at the Amazons and the Facebooks. I remember some of our kind of due diligence calls and chatting with one of our portfolio companies that was in the Martech space, and they were experiencing this as they were training their next generation of advertising technologies. And but so here you are, you sort of see this opportunity. GPUs better than CPUs, but not what you'd build if you were to start from scratch, clean whiteboard. Like, what can we build if we were to really kind of build for purpose, as it were? And did that immediately turn into wafer scale, or what was the when did you kind of say, wait a minute, like, in order to do this, we can't screw around with postage stamp sized silicon. We're going to have to go big. And when did that leap happen? I sort of feel like it was still early days, but there was, in some senses, almost a fear around saying the word wafer scale because it had been such a dangerous thing for so many companies over the last really sort of 5-6 decades. But anyway, tell us when it went to wafer scale.
I think the first thing, um, was the realization of just the unique nature of this computing problem, that was, these neural networks, in that how tightly coupled the memory, the compute, and tying it all together, it had to be able to solve this problem. Um, uh, uh, that realization, honestly, I think took a little while to get to, because the entire industry, ourselves included, was very used to this paradigm, which I guess was made popular by Google and all the hyperscalers. That all you needed to do was just scale out using these very loosely connected
Yes.
processors, right? And that was what was really driving the computing industry for the decade or two before this. And so really trying to understand, well, what is really needed for this workload, actually did take a little time to really internalize, because it was so counter to everything else that the whole industry was doing. But when you look back, it was actually very obvious. In fact, that very first AlexNet paper that I was referring to, they even needed two GPUs to right. So even like some of the very earliest models already did not have enough compute on a single chip, right? And so when we finally got to the crux of it and understood just how tightly coupled the compute had to be able to solve this problem, that's when we started to explore all sorts of different options. And you're right, there was very much a bit of a negative connotation to wafer scale. Um, we did not immediately jump there, but we arrived there pretty quickly, because once you realize how much compute, how much interconnect you need, you just start thinking through all the various ways that you can do this in the traditional way, and they're all limited, right? And it was, one day where we basically just asked ourselves, well, what if we could just build a much larger chip, right? A lot of these problems just go away, right?
Yeah, yeah. So it's interesting because you start with we the wafers are now what 12 inches ish diameter, order of magnitude, and we're basically taking the largest uh, square you can circumscribe with a 12-inch wafer. And if you think about sort of what the sort of state of the art or kind of conventional wisdom is you take these massive wafers, then you slice them into many smaller versions of that, and then spend a whole bunch of money and networking gear and copper to basically reconnect all these things and then cluster them. Right? It's like, well, what the hell are we? Why are we cutting this all up just to reconnect it again? Um, and so you basically traded that set of challenges, which comes with lots of overhead around complexity, cost, software. I mean, look, we think most folks have realized that some of the software challenges that the likes of NVIDIA have built over the last decade are more about managing what's under the covers, right? So if you could write to a single device, you wouldn't need to have so much complexity in the software layer to coordinate the workloads across so many different systems. But or so many different processors. So you see this opportunity to replace the complexity of the interconnectivity of these many systems, but we traded off a bunch of other challenges. So I mean, if I think back to some of the crazy stuff we had to do in 2017 and 18 around thermal management, stuff that today sort of feels like thank goodness we made it through that knothole. But like these were fundamental challenges around heat transfer. I remember doing some of the math, and I think on a watt per square millimeter basis, we're only off from the business end of the space shuttle rocket by a factor of about 20. So I think we're about half a watt per square millimeter. And if you're pushing the whatever STS 135 into space, that's I think about 10 watts per square mil. So I mean that's not that far off. So anyway, that's just one example of the things we had to manage. We had to deal with lots of other technical challenges. But as you look back on the craziness of the trade-offs we did choose to make as a result of building Wafer-Scale, what are the ones you're most proud of? What are the things that sort of feel like as you look back on them, it's like, wow, that was crazy hard. So glad it's behind us.
I think that you're right. Uh, the reason why this hadn't been done before is that it wasn't easy. And and you touched on, I think, the fundamental reason is that to be able to drive enough power, and then ultimately to pull that power away in the form of cooling, is a fundamentally different challenge when your chip is 60 times larger than a traditional chip. Um, and that was absolutely, I think, one of the biggest hurdles for us to be able to figure out how we can do that. And we experimented with a lot of different ideas. Um, some that are kind of seem very traditional in terms of power delivery with traditional power regulators, which traditionally are mounted on a motherboard right next to the processor. You quickly realize that there's just not enough copper in the circuit board to be able to pull enough current into the wafer. Um, and so where we ended up was a design that allowed us to mount the power regulators directly onto the wafer in a kind of a vertical third dimension. And so we are essentially driving current directly through the circuit board right into the wafer. That's an innovation that ultimately was a key enabler to this entire wafer scale integration. Another really big challenge that at the beginning we recognized, but I don't think we really internalized how big of a problem this would be. Is the problem of thermal expansion, uh,
Yes.
right?
I think
Start driving.
you'll remember the numbers better than I do, but I remember looking at the coefficients of thermal expansion between the silicon and the copper, and I was like, how the hell are we going to manage that?
Oh, exactly. And we laugh about it now, but like the number of wafers that we cracked in this in this process, as we learned how to do this and invented new techniques for how to do this, um, it was challenging. The the problem is, as uh, the wafer, the silicon is larger, as it expands, it will expand more than a traditional chip. And so we had to develop specialized ways to connect that to the circuit board, such that we would allow some variability and flexibility, so that the actual connections can actually move.
Exactly. We'll
And
keep that secret for later.
uh, that's definitely another area that we are particularly proud of, the innovation that we that went into this. In the end, when we step back, I think what really enabled us to do this and where others have failed, I think, is really our ability to have thought about the problem really like end to end, right? So this is not just a chip design problem or just a problem with the with the fab. Um, you really have to think about this throughout the entire uh, end-to-end technology stack, right? Willing to do changes and new inventions in the packaging, just to enable the chip.
I love this point you're bringing up, and I think it's one that is often overlooked. And it sort of actually speaks to your background, which would be fun to kind of unpack a little bit more too here. But you're bringing up this point of like you kind of, when you're making a very large system change, when you're inventing something that truly is new, not incremental, you really have to kind of build every component of it. And in this case, the challenges that we had to overcome around yield, so that's a hard problem unto itself. The packaging, as we were talking about a moment ago, the power and thermal management issues. And then once you get to that, then you like let's hope all that works. And then you like, okay, now how do I program this massively parallel system? So you've got to kind of take every piece of this and own it all. And I'd love to kind of have you just talk for a minute about like the kinds of people that you need to assemble to take on a system like challenge like that. So this is not these are I sometimes talk about them as missionary misfits. These are sort of folks who spike really hard in one or two domains, and oftentimes take those skills and expertise to a different domain that's adjacent, and unlock some really interesting insight that was probably not obvious to the individuals who are kind of programmed, if you will, in that domain. And so we at Cerebras, I think we've filled the building with proverbially with these missionary misfits. But talk a little bit about what's required when you take on a system challenge like this, that involves hardware, software, embedded systems, compilers, graph theory. I mean, literally, there isn't, I think, any domain in systems theory that we haven't touched, including fluid dynamics.
Fully agree. Actually, sometimes we joke about this, that we're not a startup, but we're like six different startups, right? And I think you're absolutely right. Like we realized very early on that if we really want to make a difference here, we have to design the entire solution, right? From working with the fab to obviously the chip design to building out the package, power cooling, the physical system around it, all the layers of the compiler software, all the way into the machine learning, to be able to really make a big difference. Um, and in some ways, I mean, that decision itself is a bit of a trade off decision, right? Because on the one hand, humongous opportunity when you do that. It allows you to blur the boundaries between these traditionally
Love that. Yep.
slated technologies. The flip side is kind of what you're getting at, is that it's not easy, right? Because you are effectively having to innovate across the entire technology stack, even in areas that you might traditionally think are solved problems, right? Like server design, right? I mean, that's a That's no longer an innovative. Normally, not, you don't think of that as a highly innovative field. But when you got to accommodate a wafer-sized chip in a package, well, you got to rethink that as well. And so you're right. The only way to to make that work in our minds is you need to surround yourself with incredible talent across the spectrum. Um, and you hit on a very key characteristic that most of our engineers have, which is not only are they experts in their field, uh, they have to have the mentality and the open mindedness to be able to work in this kind of boundary between this particular field and the adjacent field. Um, and be able to be fluid around that. We pride ourselves in having a very vertically, co-design mentality team here, without which we this would would just not be possible.
Yep. Yeah. Yeah. So let's shift gears and talk a little bit about some of the software challenges. And we've got now this extraordinary platform, Wafer-Scale Engine 3, which we announced about a month ago or so. Just as a reminder to folks, this is the largest and the fastest AI chip. Roughly 900,000 cores, 4 trillion transistors. Um, Sean will hit on, I'm sure, some of the other ridiculous, memory specs and things like that. But here's this system, and I think probably the one that most excited me was just the fact that we could cluster 2,000 of these things, which is just mind blowing. And I know we will have customers and partners that will actually do that. So the fact that it can be done will probably mean it will be done. But so you got this amazing piece of infrastructure, and yet the thing that I think makes it most interesting is that it really can be addressed as a single device. Is that instead of having to, as a machine learning or AI engineer, have to sort of figure out how to lay my model, my big model that hopefully I'll be able to iterate quickly onto this hardware, is just insanely simple. And the sort of philosophy behind that, in other words, the hardware affords new approaches to the software. And I'd love for you to kind of talk about what that means, what that has unlocked, and maybe give a few examples of some of the ways that it's kind of even excited you or surprised you to the upside.
No, yeah, absolutely. I think uh, for folks who haven't done this before, running ML models on large GPU clusters is really really hard. I mean, to the point where uh, uh, almost every large model is a really big research publication, right? And companies like OpenAI and Google have teams of hundreds of people not doing the ML but doing the distributed systems engineering to figure out how to map that ML onto hundreds or thousands of GPUs. And at the heart of it, the reason why you have that challenge is actually pretty simple. When you're taking this really really massive model and you're trying to fit it on a bunch of these tiny little devices, you're just using the wrong tool for the job. And so a lot of what how we think about the problem here at Cerebras, coming back to this whole co-design and vertical design, is you got to right size the problem and right size the tool for the problem. Um, and so a key capability, since our chip has so much performance and is so large, is that we can actually run the entire state of the art large model on a single chip.
Love that.
Right? And so you can do that, and then once you can do that, then you no longer have to split the model. Then to get acceleration, all you have to do is then replicate, right? And that's what's called data parallel replication. It's actually very simple. You're literally just copy pasting and replicating the model and running it all in parallel. And we've built an entire cluster architecture, custom built with exactly just this model in mind, so that, as you said, from the user's perspective, right, whether it's one system with one wafer in it or hundreds or up to 2,000 in our current generation, the programming model looks exactly the same. Um, and that's really been revolutionary. And is really one of the key enablers for what our customers have seen. And you were asking, like, some of the things we're most like excited or proud of. We've had customers who have come to us and they say, hey, we can't, we have a ton of GPUs, but we can't get the problem to scale beyond 64 GPUs. We
Yep.
tried it on 128 and it doesn't run any faster, or the model doesn't converge any faster. Well, why is that? Because it's very hard to take that problem and split it up into 128 small pieces and have them all coordinate and communicate with each other in a way that you can continue to get speed up. And then that same model that they could run on 64 processors took them 2 months to train this particular customer. On our cluster, we trained the whole model in, like, I think it was 3 days or something.
Yeah, it was a long weekend. I remember this.
Right?
And I think they actually didn't even, it wasn't done at 70 days. So it was still working away. Um, I mean, you had said something to me, this is maybe a month or so ago, and it actually reminded me of kind of the early days of the company and some of the observations around these workloads really exploding much faster than Moore's law could keep up. But if we just look at from when we launched at Hot Chips, this is the Wafer-Scale Engine 1 in, I want to say, August of 2019 to today, so almost 5 years. The compute requirements have grown, I think, by 40,000x. Is that roughly where we're at? Yeah, crazy.
That's absolutely right. Back then, the most state of the art language model was BERT. And today, if you consider GPT-4 as the state of the art model, to train those two models, there's about a 40,000 times difference in terms of overall training compute. It's
So do you
insane.
think the next 5 years look like an extension of that? Is it another 40,000, or do you think it's 400,000?
I think that it wants to be another 40,000 or more, but I actually think that this is a fundamental problem that our entire industry is facing, because using the current approaches, I don't think there is another 40,000.
Math doesn't work. Basically, the
At some point, you're gonna be deploying like multiple football fields worth of silicon just to train a single model, and spending tens or hundreds of billions of dollars just to train a single. It's just, at some point, it doesn't, right?
and we haven't even talked about the power requirements, right?
Power is yeah, exactly, right. And so I think that is the fundamental challenge that the whole industry is facing, and very much at the heart of what we are trying to solve here at Cerebras.
Get it.
Uh,
Got it. Maybe I want to switch to sparsity in a minute, but you're reminding me of sort of this concept Carver Mead had. This was this sort of call to action that he had in 1980 when he told engineers to basically waste transistors, right? So Carver was one of the sort of one of the fathers of neuromorphic computing, and had this kind of concept of very large scale integrated systems, and this concept of wasting transistors seemed a little odd at the time, but if you think about what was possible in terms of going, for example, from command line interfaces to GUIs, when I think about some of the programming I did when I was a kid, it was like you had to be so careful and sparing in your use of memory, that the idea of moving a mouse around to then effectively move a cursor on a screen would have been the most wasteful, really sort of just computationally irresponsible thing to do. But when you can waste transistors, you can begin to unlock some very interesting use cases, things that would have been foreclosed, and it just sort of lights up a world of creativity. I think about sort of what we're doing in some senses as another version of that sort of waste training. In other words, being able to not have to this point, train over the course of 70 days, but be able to train much more quickly, in hours, maybe minutes at some point, such that you can build more models, experiment with more ideas much more quickly. So anyway, I realize it's a 40-year-old metaphor to tie back to Carver Mead, but I think there are some interesting parallels. Maybe shifting gears, because I feel like one of the other innovations that we really have pioneered with the Cerebras system, again, this is less about the hardware and more about the system, is this concept of sparsity, and taking advantage of The fact that we know a lot of matrix multiplication is over parameterized, is there's kind of too many to many math computations, lots of math that only results in the number zero, which maybe we shouldn't be doing. But just talk a little bit about what we're doing in sparsity and why it should matter.
I think you're absolutely right. In a lot of ways, when you think about what neural networks are and what the process of training a neural network is, what it is essentially created. You're creating a very over parameterized model, a model where you're throwing a lot more parameters in there than it actually needs, and the process of training is in some intuitive way discovering which of those parameters are actually important and which are not, right?
Right.
And even if you look at the actual structure of these neural network layers, they're actually these all to all connected layers, these neurons where every neuron connects to every other neuron. And that's because when you start off training, you don't know which ones are important, but over
Exactly.
the purpose of training that model is to discover, the values and which of the those parameters are actually important. And so sparsity, this concept of being able to have parameters that you can remove from the model, is what sparsity is. It's very inherent in the neural network architectures themselves, and and it's an area that I think is generally well understood because it is intuitive. However, the way that these models are implemented and executed on traditional hardware like GPUs doesn't allow you to take advantage of the sparsity. And the reason for that is, as you alluded to, is that GPUs and even other popular accelerators like TPUs, they're basically dense matrix multiply engines. They
Yeah.
put a ton of flops in there to be able to do dense matrix multiply. And that means that they can't actually accelerate if it turns out that a bunch of the matrices have a bunch of the elements within the matrices have zeros in them. They're going to go right ahead and multiply and add by zero, and guess what? Multiply and add by zero doesn't change the answer.
That's an interesting math. Let's not do that.
You don't need a PhD in AI to know that, right? And but it's very hard for a matrix multiply engine to be able to extract out these zeros. And so we had that observation very early on, and coming back to this whole concept of designing a hardware platform from scratch for this workload, we knew it had to support sparsity because these models have so much inherent sparsity. So we designed our hardware to be able to accelerate unstructured sparsity. These zeros can be anywhere within these matrices, and every time you see a zero, not only do we save the power because we don't execute it, we can accelerate and skip it and move on to the next non-zero element, and you get speed up. And coming back to your earlier point about the 40,000 times more compute, I believe that sparsity is one of the key ways for us to be able to get there. If you
Yeah.
just brute force dense matrix multiplies, it's going to be very hard. But we can make the computation much more efficient by skipping all of these redundant parameters. And we're very proud that we had this insight at the very beginning, and right now we're the only commercial AI accelerator that accelerates unstructured sparsity. And as I said, not only is it producing acceleration now, I really believe that this is one of the vectors that will enable that next big step for the whole industry.
I'm so glad you unpack it. I mean, I think about we're known particularly because the hardware is so impressive for chip architecture, system interconnect fabric, data I/O, lots of reasons why we're getting so much more at the hardware. But data sparsity is when I think about our vectors of innovation is actually the largest lever, and it's also the one that I think has so much more room to run. Maybe if you could, without kind of getting into to the realm of the proprietary, but are there other vectors of innovation that you're excited about exploring that are we're pursuing? I mean, I think about numeric representation as another area of opportunity. We don't talk much about that, but what are some of the other vectors where you think we can kind of maybe gain purchase on this opportunity to deliver more benefits without having to 400 or 40,000x compute requirements.
I think I think numerics is a good example. Obviously, we spoke about sparsity, but I think these all fall under this kind of broad umbrella of ML co-designed with the hardware, right? Thinking about changes you can make in the ML algorithm that would allow the hardware to be able to operate a certain way, right? Or changing the way the hardware operates to allow the ML to explore different architectures. I believe that that's where the next wave of big step function improvement is.
Yeah, yeah.
Be.
You're another sort of towering figure in the field of computing, Alan Kay, right? If you're really serious about software, you got to make your own hardware. So, and you're bringing up this point around, if you really, really want to challenge the kind of the old approaches, you've got to be willing to kind of work at every level of the stack. Maybe just shifting gears. Do you see any other big opportunities kind of in untapped opportunities in AI hardware? We're obviously working on a very, very substantial one with Cerebras, but when you advise entrepreneurs or sort of see interesting things and people try to grab you at the end of a keynote and tell you about their cool idea, what are some of the things that you are excited about or at least curious to learn more of?
Yeah, I think there are a few areas that I'm really excited about, and not surprisingly, they all kind of fall into this kind of co-design space. Um, Pushing numerics to the extreme, I think, is very interesting. Um, right, we know that even in standard hardware today, people are talking about training in 4-bit math. I think you can push it even further, but
Yeah,
you can't do that without making changes on the ML side, right? But I think once you do 2-bit, 1-bit models, they start to become, promising or viable. There are other ideas that or just general kind of space where I feel like there's a lot of promise is um, in more dynamic models, right? So today these models are generally static. They're generally known exactly upfront, right? Oh well, the llama model has 80 layers, and each layer is exactly this size, and it has two feed forward sub layers and so on. And all you're doing is you're basically just running data through it. I think there's a very promising vector where you can change the shape and the size of the model based on the data that runs through it. Um, Imagine a world where the depth of the model changes based on how complicated the data is, right? If the data comes in and it's actually relatively simple, well, maybe you don't need such a deep model, right?
yeah, you're right. So it's sort of simple, complex, possible. Kind of
Exactly.
does again back to this notion of sort of let the system sort of scale with the workload.
Exactly. So that's another area where I think even intuitively you can see where where there might be promise, but it's not actually easy to be able to run those types of models on existing hardware. Again, because of this rigid matrix multiply engine underlying core, right? And so another one of these opportunities for hardware ML co-design. So I think there's a very rich space here that can be explored that often is not explored because there doesn't exist the hardware to explore it on, right?
Yeah, yeah. So maybe in the last few minutes before we let you go, would love to just kind of gather some of your thoughts and advice for entrepreneurs who are kind of early in their journey. So imagine the 2016 version of Sean, just as you were starting Cerebras with Andrew and crew, and kind of what you've learned about building a deep hard tech startup, all of the sort of challenges of I'm sure uh, yielded some epigenetic rewiring of your brain. What are some of the things that you would sort of like to pass on to the younger version of Sean?
Uh, that's a great question. I think if I if I were to rewind, I think the first thing I would I would warn myself is that
Don't do it.
a version of that. This is hard. Doing deep tech startup, especially at the kind of scale that we're talking about, is hard. This is by far the hardest thing I've ever done, right? And it's not for the faint of heart. Um, uh, but I think in terms of advice, I think the advice there is really you know really understand what you're getting into, right? We made a very conscious decision that we're going to go after this really massive problem, and if you're going to do that, make sure that you're set up to do it across the board, right? And this isn't just making sure you're hiring the right people. That's a huge part of it. um, I think it's making sure that you set up the rest of the business, to support it. It makes sure that you're working with the right investors and the right and who understand ultimately what you're trying to go after. Right. It affects the business model that you're trying to build. I think one of the lessons that definitely probably took me a little longer to learn, coming at this, especially from the technical side, is that obviously deep tech startups it's all about the technology, but it doesn't work unless you have all the other supporting and surrounding infrastructure, so to speak, right? And and making sure that you think that through upfront, right? And that's something I think I'm pretty proud that we were able to do that from the very beginning. um, and it meant we were able to hire the right people. We were able to work with the right types of investors like yourself, um, the right types of customers and early almost partners.
Yeah,
uh,
yeah, they've been. I mean, there's if you think about sort of how important it is to choose the right, highly aligned design partners who are going to forgive you when the thing doesn't work perfectly, and in fact, in some senses, become an extension of your team. You're reminding me too a couple of thoughts. As I think about some of the lessons to pass on to kind of the next version of Sean, who we want to meet, by the way, is I think lots of folks work on deep tech, hard tech, frontier investing, and forget that it's not just supposed to be hard to do, but it must be worth doing, right? So I think one of the things that I'm so proud of you guys, and it was so clear from really day zero, was we weren't going after 20% better, 50% better, even 10x better gets chipped away at relatively quickly, as we know in this domain. It's like you've got to be three orders of magnitude better for it really to matter. And you guys went after that. The very first versions of what we were building were that kind of the simulations we were running were 1,000x better. And so I think that really matters. And then the other one I think I realize, and it kind of ties back to some of the sort of thermal management challenges we were joking about that at the top of the podcast, was just um, debugging very complex systems issues is a very tricky thing, because it turns out that the big problems actually hide smaller ones. They lurk in their shadows. It's like there's when you solve the big problem, there's another set of problems behind it, but you couldn't have seen those ones behind it until you solve the big one. So like just kind of rushing to the fight, if you will, with the biggest problems, and as quickly as you possibly can, so that so that you'll then discover the ones that are hiding in the shadows right behind the big ones. So those are a couple of quick thoughts. I guess unless there's more advice for entrepreneurs, I'd love your thoughts on when you think about this massive stepwise shift towards towards AI and all of the massive markets that it is going to influence and disrupt. Everything from energy and healthcare, and these are things that are 15-20% of GDP kind of markets. And when you think about kind of decades from now, how will this moment that we're living through, kind of this last 5 years, in the next 5 years, how will this be remembered, and kind of what excites you about what will be possible maybe in 5 years that we couldn't even imagine when we were, if we'd done this podcast in 2019, 5 years ago.
yeah, absolutely. I think that uh, there's maybe two general ways that I think about that, right? There's the societal impact that this is going to have, and even if I take the Cerebras hat off, right, the time that we're in is, without a doubt, some pretty magical, time. It's a once in a generation kind of, or multi generation kind of time. And what's so exciting here is that, like you said, I think this is going to enable capabilities that we can't even imagine right now. And we're kind of in this, like, I think, super early phase, uh, where AI is kind of interesting in that it's a type of technology where it's like super easy to come up with a bunch of very simple use cases, because pretty much, like, anything that you can think of that you or I could do, we would like, oh well, maybe there should be an app or an AI that could do that, right? I can write emails, I can do marketing, I could do, right, I can write tweets, I can meet an assistant, it can, but I think what's gonna become, the real impact is when we go beyond those kind of trivial things, and it's helping us solve, like, healthcare problems that, like, we wouldn't even be able to solve, without it, right? Things like that, which I think are going to have the lasting societal impact. So that, that's my bet, and why I'm also very excited that we get to play a small part in being able to enable this future. Now, from a technologist standpoint, or outside of the general public and society point of view, as a technologist, I think that this time is going to be remembered as a time when, kind of the hardware innovation has been reborn. If you think about hardware, and chip design and processors 10 years ago, um, I was in that field. Kind of boring. Right? I mean, yeah, you're making incremental improvements every generation to generation, but uh, not really enabling anything new. And now we're in this like era where, without the hardware, you wouldn't be able to enable the ML, right? And I think, there's a reason why almost every big hyperscaler is building their own hardware. Um, and I think that's one of the big transitions that this whole kind of modern AI, um, field has brought on, is this resurgence, rebirth of the importance of hardware. And I think that's a great thing, especially given I'm a hardware guy, right?
Love
Um,
that. Yeah, and I think it gets back to this point of the interplay between hardware, software, embedded systems, and this notion that you really, I mean, these iterative algorithms, you were kind of alluding to this before, they're just super special in that they can lead to these very complex artifacts that actually transcend the complexity of their antecedents, right? So they create opportunity that couldn't have been predicted, and you need not just the algorithms, but you need the hardware to be able to enable that. And of course, we won't always understand how they're doing it, but and we've got to gain purchase on that specific topic. But I agree with you. It's the full stack that kind of enables all of this to be possible. Awesome, Sean. So great to hang with you. Are there any other resources? Again, this is in the spirit of educating the next generation of entrepreneurs hoping to follow in your big footsteps. But what would be, are there any books, podcasts, Substacks, anything that you sort of would point folks toward that would help them on their journey?
I guess that's a great question, and I guess I'll start off by saying that I'm not generally the kind of guy who reads books and listens to podcasts about business, or building startups and so on. But I guess, if I had to pick something here, I will say that, um, uh, and this actually comes back to, even I think, as I look back, a lesson that I myself, feel like I learned the hard way. Um, uh, Reid Hoffman has a great podcast on scaling, uh, right? And as I think back, uh, early days and even very recently, one of the things that I think has been the hardest uh, is, is figuring out how and when to scale, right? And that's the product itself. That's the team, right? I can't do it all myself. Um, there's only 24 hours in a day, and I need to sleep for a few hours. Uh, right? Uh, that's scaling. Our customers and the business. Um, I think one of the things that I feel um, many entrepreneurs, myself included, um, uh, don't think about early enough is planning to scale, and I think that's something that I would tell any aspiring entrepreneur, that not to say that you need to be scaling out of the gate, but you need to be thinking about it. You need to be preparing. You need to make sure that what you're doing doesn't lead to a dead end, that you then have to redo everything to figure out how to get to the next level.
It's a great point, and I think relates to. I mean, I think certainly something that's important in our business on the investing side, but it relates directly to the point that you're bringing up, which is, there's a timing element to so many of these opportunities. I mean, we obviously spent a lot of time understanding the market opportunity, and we talked about sort of how the compute and AI workloads and ML workloads were exploding back in that kind of window between 2013 and 2016. But I don't think, I mean, we couldn't have predicted, the next inflection after AlexNet, was really Transformers in 2016, and there's just ridiculous, acceleration over the last handful of years as a result of all of that effort. And so, it's very hard to make the waves. It's impossible nearly to make the waves, but you want to be ready to ride the wave and ride the front half of the wave, because climbing up the back half of the wave is pretty darn hard. So, but yeah, and I'm just so excited by what we're doing at Cerebras. Before we started this call, we're riffing on some of the things we're going to announce over the next couple of months, and more to come. So hopefully folks got something out of this podcast. Sean, I'm hugely grateful for all the time you spent with us, and for all the work you've done at Cerebras, and the leadership on some very gnarly technical challenges. And we'll continue to innovate and launch some amazing things. And for anyone out there looking to get a hold of Sean, you can find him in lots of usual spots. But let us know if there's anything that comes up, and we'll follow up in the comments on this, and look forward to continuing the conversation. But thanks again, Sean. Great stuff, and congratulations on all the amazing both technical and commercial success you've been helped drive over at Cerebras.
No problem. Thank you, Steve, for having me today, and of course for all your support over the years here at Cerebras.
Awesome. Thanks, man. We'll talk to you later.